Hello and welcome to Controllers Tech. A lot of you guys requested this, so today we will finally cover one of the benefits of using the FSMC peripheral of STM32. The FSMC stands for Flexible Static Memory Controller. It is an embedded external memory controller that allows the STM32 microcontroller to interface with a wide range of memories, including SRAM, NOR flash, NAND flash, and LCD modules. As I mentioned, we will use one of its benefits, and that would be using the FSMC to interface the LCD module with the MCU. We can use the FSMC to interface the LCD in the parallel mode, be it with 8 data pins, or 16 data pins. It gives us an advantage that instead of performing the normal GPIO operations to push the data to the LCD, we can simply assign the data to the FSMC memory, and let the peripheral do the pushing. I will cover this topic in 2 parts. Today we will see the connection, the pin requirements, how to implement the FSMC with the display library, and finally we will turn on the display and run something on it. In the next part, we will add the touch interface, along with the LVGL to our project. This will make it easier for us to add complicated things to the project. I am going to use the STM32 F412G discovery board for this project. The reason is simple, it has the LCD connected to it using the FSMC. I don't have any LCD device with me that uses the parallel mode, so I decided to use this board. We will check out the pin details later in the video. Here we have the schematics of the same board. This is how the LCD is connected via the FSMC. The display uses 16 data pins, along with the other pins required by the FSMC peripheral as well. Now before we go on with the project, I want to share an important detail. A lot of popular display libraries are already available in the ST's database. You can access them by browsing the STM32 Cube folder on your computer. Open the repository folder, and here you can see the firmware packs for different series. Now open the firmware pack, and look inside drivers, BSP, components. Here you can get the library of different components used in STM32 F1 series boards. For example, we have the library for the LCD controller 8347D, ILI9320, 9325, and ST735 as well. All these libraries use the same structure, so if you get familiar with one of them, you will be able to interface other displays as well. Now if we look inside the F4 firmware pack, and again open the BSP components folder, you can see other libraries also. Here we have the popular ILI9341. Now the display I have on the board uses the ST7789H2 controller, so let me copy the library files to the desktop first. All these display libraries have the same structure. Let's take a look at the 89H2 library. Here we have a function to initialize the display, another function to set the display orientation, functions to turn the display on and off, etc. The functions contain the command and data to perform the respective operation, but they do not send the command to the display. Instead we have the LCD I/O functions to do this job. These I/O functions connect the library to the display. You can see we have the I/O function for initialization, and another one for delay. We also have the function to write the LCD register. Basically we just need to define these I/O functions in a separate file, and use the appropriate method to send the command and data to the display. The method depends on how the LCD is connected to the MCU. We can use the normal GPIO operation, the FSMC, SBI, or I2C, however the display is connected. I will demonstrate this in a while. Let's create a new project in the Cube IDE. I am using the STM32 F412G discovery board. Give some name to the project and click Finish. Let me clear the pinouts first. Alright, let's start with the clock setup. The board has an 8 MHz crystal on it, and I am running the system at a maximum 100 MHz clock. Go to sysdebug, and enable serial wire. Now let's configure the FSMC peripheral. We need to select the chip select pin first. Let's check the pin details in the board's datasheet. The chip select pin of the LCD is connected to the FMCNE1, which is the pin PD7 of the MCU. You can see the pin details in the schematics also. Let's set the chip select as the NE1. Here you can see the pin PD7 got selected as the NE1. The memory type is the LCD interface. Set the register select to A0. This is as per the connection shown in the schematics. The register select is used to tell the LCD whether we are going to send an instruction or a piece of data. If you are using an external LCD, you can choose other values of the register select as well, depending on how you are connecting the LCD. But in my case, the LCD is already connected to the board, and the RS pin is connected to A0. The LCD uses 16 data pins, so select it here. Now we will configure the FMC pins. I am going to configure the data pins as per the schematics. Alright, all the data pins have been configured. The initial part of the configuration is kept to default, but we need to configure the timings here. You can get more information about the timings in the application note AN2784. This application note actually applies to the STM32 F1 series MCUs, but we will just take the important points from it. Here we will look in the NOR flash section. As shown here, if the main AHB clock is 72 MHz, we need to calculate the AHB clock cycle, which will be 13.88 nanoseconds. In our case, the main clock is 100 MHz, and hence the clock cycle will be 10 nanoseconds. Make sure you calculate everything in nanoseconds, as we would do the calculation in the same unit. We need to calculate the address setup time, data setup time, and the bus turnaround time. Out of these, there is no formula to calculate the bus turnaround time, but we can calculate the other two. Here you can see the conditions these parameters must satisfy. And here we have the formulas to calculate them. The address setup formula requires the data setup value, so we will start with the data setup first. We need to know the two values to calculate the data setup. This here is the main clock cycle, and the WP timing is basically the time required for write enable high to write enable low. You can find the timings in the datasheet of your LCD. Here I have the datasheet of the ST7789H2. Just search for the term timing. We should look under the timing characteristics for the parallel interface. Here we have all sorts of timings required to interface this LCD, but I don't see the same for the write enable high to write enable low. On the other hand, we do have the control pulse high and low durations. I will just take the average of these two values, and use it as the WP timing in the formula. So we have the WP timing at 15 nanoseconds, with the clock cycle at 10 nanoseconds. The data setup time will come equal to 1.5. I will set it to 2. Next we have the formula for the address setup. We will first calculate this much part by using the WC timing and the clock cycle. The write cycle timing as per the datasheet is 66 nanoseconds. If we divide it from the clock cycle, we get 6.6. Now we will subtract this part from the result. The data setup value is 2, so we will subtract 3 from the result. To calculate the address setup, We will finally subtract 1 from the result. We got the value 2.6, so I will use 3 in the setup. There is no formula to calculate the bus turnaround time, so I will just set it to 2. That is all the configuration we need for the FMC. If the display does not work with this configuration, we will change it a little. Other than data pins, we need to configure a few more pins for the FSMC. The LCD tearing effect pin sends an interrupt to the STM32, and this is connected to the pin PG4. So let's enable an external interrupt for the pin PG4. The read pin of the LCD is connected to the FMC NOE, which is the pin PD4. The NOE is already enabled, but we will map it to the pin PD4. Then we have the right pin connected to the FMC NWE, which is the pin PD5. The pins R, S, and CS have already been configured. The reset pin is connected to PD11. Let's set this pin as output, and we will rename it as LCD reset. Alright, that is all the configuration we need. Click Save to generate the project. Now first of all we will copy the LCD library files to our project. So copy the C file to the source directory, and the header file to the include directory. Let's take a look at the source file now. This LCD driver structure is common to all the LCD libraries created by the STM32, but I am not going to use it, so let's comment it out. Let's remove this inclusion from here. As I mentioned, we need to define a few LCD I/O functions, so to connect the library to the MCU. Here are all the functions we need to define in a separate file. Let's create a new header file in the include directory, and we will call it LCD controller. Inside this file, define all the LCD I/O functions, but not as the external variables. Let's include the main header file for the necessary inclusions. In the display header file, include the LCD controller, so that it can fetch the LCD I/O functions from there. Now create a new source file in the source directory, and name it lcdcontroller.c. Here we will write the code for all the LCD I/O functions. The content in this will vary based on if you are using SPI, I2C, FMC, or any other method to interface the LCD. The FMC memory region is defined in the MCU itself, and it is common for most of the MCUs. But I would advise that you still check it once before proceeding further. It can be found in the Memory Overview section of the reference manual of your MCU. Here you can see the FMC memory starts from 60 million hex. Just like we have different methods to send the data and command to the LCD using different interfaces, we also have a method to do the same using FSMC. The memory addresses for the command and data need to be different here. We will first define a memory location for the command, and I am calling it FMC Register Bank. Here I am setting the memory location at the start of the FSMC address. The register select is responsible for selecting the register for writing data or commands. If you remember, the register select is set to A0 in this case. And therefore the memory location for the data will start at an offset of 2 from the start. This is something you need to understand in detail. There is not much explained about this in the manual. Here you can see for 16-bit memory width, the internal AHB address line considers the address from bit 1 to bit 25, which is then shifted to the right by 1 place. Let's understand this in detail. Here I have the picture explaining what happens inside the AHB address line. This here is the 32-bit AHB address line. For 16-bit memory width, the bit 0 is not considered at all. The addressing starts from bit 1. And we have a total of 25 bits, starting from 1 to 25. So if I use the register select as A0, this is actually seen as the bit 1. Now to send the command, this bit should be 0, and to send the data it must be 1. This setup will make our least significant 4-bit nibble as 2 hex, while sending the data, and it will remain 0 for the command. The higher 4 bits of this 32-bit address are used to select the FSMC bank. We are using bank 1 for the NOR flash, so this data will be fixed to 6 hex. You can see the details in the image shown. The bits 27 and 26 are used according to the chip select pin. For one particular bank, the combination of these bits selects different CS pins. Then the rest of the 26 bits are configured based on which register select signal is being used. All these 32 bits together makes the address for the command and data. Assume that I have selected the A4 signal for the register select. For the 16-bit memory width, the bit 5 of the address line will be configured. This will make the data address offset as 20 hex. The logic discussed so far does not work if the 8-bit memory width is used. For the 8-bit width, all the 26 bits of the address line are used, and hence the counting starts from 0. You can see it being mentioned in the reference manual also. So if you are using 8 data lines for the LCD, and you have selected A4 as the register select, the bit 4 will be configured for the register select. This will set our data address at an offset of 10 hex. So I hope you understood how the register select works here. We now have the addresses for the command and data, so let's start writing the functions. First we have the initialization function. Many LCDs might not need this, but just to keep things perfect, we will write one for this one. Here we will just handle the LCD reset. So first reset the pin, wait for a few milliseconds, set the pin, and wait again. This will complete the LCD reset. The reset of the initialization will be handled by the LCD library. Next we will write the function to send the register address. Here we will just copy the register address to the register location in the FSMC memory. Then the function to write the data. Here we will copy the data to the data location in the memory. To read the data, we will simply return the value from the data memory. Now we have the function to write multiple data. Here we will call the function to write the data, as many times as the size defined in the parameter. Each time, we will pass a new data value from the given pointer location. At last we have the delay function. Here we will just call the whole delay, and pass the parameter delay to it. Let's write the main function now. We will include the LCD library file here. Now in the main function, we will initialize the display first. Let's build the project to see if there are any errors. Everything is fine, so we are good to go. Here you can see all the functions available for the display. To check the simple working, I just want to fill the display with some colors. But here we don't have any function to fill the entire display with a color. We have a function to draw the horizontal line, so we will simply draw the line throughout the display. Let's write a function in the main file, whose parameters will be similar to this line drawing function. Now inside this function, we will keep drawing the horizontal line of the given width, for the given height. In the main function, call the function LCDFill. Let's give some random color code here. The drawing starts from the position 00, and it shall draw for 240 pixel wide, and 240 pixel height. Let's give a delay of 1 second, and fill in another color. Here I am displaying 4 different colors at an interval of 1 second. Alright, let's build and flash the code to the board. There seems to be some error, and the display is not turning on. Actually I missed the configuration of the LCD backlight control. It was not there in the main image, so I might have missed it. Here you can see the LCD backlight control is connected to the pin PF5. Let's open the Cube MX, and set the pin PF5 as output. We need to set this pin as high, which we can do in the code, or we can also do it here. Let's generate the project again, build and flash it to the board. You can see the LCD is getting filled with different colors. The colors are switching every 1 second, and our code is working fine so far. Let's try to display some known color values. Search for the 16-bit color codes. Here I will display the pure red, pure green, pure blue, and the yellow color. Let's build and flash it again. You can see the LCD is displaying the respective colors. So we got the LCD working using the FSMC mode in STM32. You can connect any parallel display to the MCU using the FSMC, given that the MCU supports the FSMC. This is it for the video. I hope you understood how to configure the FSMC, and how to interface the display with the MCU using it. You can read the details explained in this video from the link in the description. The project can also be downloaded from the same link. This is it for today. Keep watching, and have a nice day ahead.